So we had this problem yesterday of let me do this of M and then K, big M, little a, little m, and we said this is a model. It's a linear model of CO2. Yeah. And again, you could say, well, how can you even begin to do that? Well, if you were to have two atoms here, A and B, like this, so let's say this is R. If you were to plot the potential energy, V of R, how does it look like for two molecules? Kind of has this shape here like this. Okay. That's what almost all two-body interactions look like at some level. I mean, you have what the actual shape is, it's important, especially if you're doing modeling, molecular dynamics, stuff like that. But if we're right here, about this point here, what does it look like? This potential. It looks like a spring. So if you're looking at the motion right about here, it's very appropriate to then allow these bonds as springs. That makes perfect sense. So we wrote our K matrix and we wrote our M matrix. So our M matrix became this happy little thing of M0, 0, 0, big M, 0, 0, 0, little m. And for almost anything, we're going to have it always go. And then you to work it out formally, you have to use that one expression. So formally. Okay, remember that these MJK elements are given by, what are they given by again? Summing I going from 1 to n.
Mi.
Okay, mi. Partial R vector I with respect to Q,
J.
J, dot. Partial R, partial I, vector to Q, K. And so what happens here is, or actually you can kind of figure it out, is that basically these things are going to really go to critical examples very often. So what happens is we can send a listing value like that. Okay. Well, formally, what you do if you have something weird that didn't look like this is how you go through the approach with that. But almost all cases that you're going to be coming across, if you do this formally, you end up with just that the mass is along the value. Okay, then we worked out our potential here. When we worked out our potential, we had a whole bunch of terms here. What did this end up becoming? Actually, what did this end up becoming? 2K minus K 0 minus K
2K.
2K here. This is K.
Yeah, it's just it.
This is K. 2K minus K 0 minus K. That what we had. Then we set up our little handy dandy determinant. That and set it to 0. And we ended up getting our omegas here. I'll set it up again. So if you do that, I'm trying to solve it. You get this minus omega squared little m plus K minus K 0. And then minus K minus omega squared big M plus 2K 0.
That was a minus K.
Yeah, that's it. Thank you. Yeah. 0 minus K minus omega squared little m plus K. This equals 0. And how did I tell you to do this? Almost always, especially with the food bar 3. Yeah, do it with the okay, that's the technical name for that. Don't do, I mean, it's not wrong to write it like the mathematicians do, where they say, expand actions with the cofactors. That's correct. The problem is that's going to give you something that very frequently won't be obvious on a factor. And when you do these things, never multiply out this whole thing here. to multiply out this whole thing here, you're gonna get a quadratic, you're gonna get an equation in omega to the 6th. All that's going to happen. You have to factor this in. Okay. And so when we do that, what did that give us? That gave us basically, we ended up with 3 modes here. We ended up with this guy. We ended up with that being one mode. We ended up with this being another mode. And then what was the other one? I don't remember what it was. Don't really want to work it out. Okay, so this one here gave us this omega squared equals k squared. And this one then, the last omega squared was
K times.
K.
parentheses, 2 little m
k times parentheses 2 little m plus big N
minus. big M.
minus that one
Minus big M.
minus big N.
Over little m big M.
Little m big N. Okay. No, I like that. Right. Okay, to be honest, I don't know what they are. Okay. That little minus sign doesn't make me happy. Plus.
Means.
Plus makes me happy. Minus does not. So we're good. And so they're the 3 ones we have here. And so this is one of the new features no one would talk about, and we already mentioned it. What did we say this corresponds to? Yep.
Translation.
Of the entire molecule. So if you have that whole molecule moving where nothing's vibrating, it's just pure translation. That's what this corresponds. So the omega equals 0 corresponds to a pure translation. No vibrations. Of the entire molecule. Now we don't care about that in there, so we just throw. We just say fine. We can just throw it out. Again, pictorially complete this. Be this whole thing here just moving this way. That's what that correspond to. We know that because if we look at these etas here, these eta i's are this eta I naught, you know, the I omega t. We put in the omega equals 0 here, this just gives you 0. And these are from the displacement here, meaning that the whole thing is just shortly, not doing anything. Okay, that makes sense. So we kill that one there. But whenever you have these free molecules like that, you're always going to get those. You're going to get that motion, and that one you just have to throw out. Okay. Now these other ones here. What do these correspond to? So how do we say we go about finding what this corresponds to? The what? Motion. Did I give these names 1, 2, 3 yet? Okay, let's give these names. This is the first one we found. We'll call this 1. This is the second one we found. We'll call this 2. This is the third one we have. We'll call this 3. Okay. So what motion? Let's say what motion does omega 2? I'm sorry, omega 1. What's the motions do? Omega 1 and omega 3 correspond to. Okay. Now we already said this, but let's go through and do it. So what are the other motions? Yes, we're gonna have basically this is gonna be stationary, these are gonna come in, and then these are gonna move, and then this is going in the opposite direction. The higher frequencies always occur to the one where things are kind of moving in. We're not all moving in sync. So which one of these do you think corresponds to this one? And which one corresponds to, this going this one, this one?
Omega 1 is.
Omega 1's gonna be this guy. And then the one where these are going this way while the middle guy's going the other direction, that's going to correspond to the higher frequency. That's usually the way it always, well, this way it always is. So we want to figure out how that goes. So how do we go about finding those again, that motion? You have to go back one step. So we go back one step to remember that our original equations are in this. That's our original equation. So we have to go back to this form here. So if I had to write this out, this would be our omega squared m plus k minus k 0 minus k minus omega squared big M. It's 2k minus k minus omega squared little m plus k minus k 0 here. All times in the desired for this one. Better that one. Can't be recycled, but it is in a bin. That's the important. I'm tired of that. I'm glad it returns by itself. Well, it's at least in the corner. Okay, so if I take the average of those two positions, it's in the best. That's the important. Okay, so what did I put in here then? A, B, and C, because basically it's going to be, this is my eta right here. I'm saying that this eta here, I have no idea what it's going to be, so I'm just going to call this A, B, and C. Okay. Again, these would all have the same e to the I omega t's on it. That's what I'm doing that part. So what do? I now put in for this guy here. So we're going to sub in omega 1 squared equals kilogram. So what does that give us here? So that gives us I didn't read that matrix in the absolutely giant form. I'd actually have no room over here. I'll make it a little smaller. So this gives us what? If I put in this k over m here, what's gonna happen? I'm running out of room, so.
Then goes on.
Okay, so the m goes out, leaving
Negative k.
minus k, which is gonna find this and giving 0. So I'm just gonna write to 0. Okay. This is gonna give me 0. Minus k 0 minus k. What does my buddy do? My buddy here do? My middle guy goes
Negative big M over M K.
yeah, minus that. K little m big M. It's 2k like that. Yeah. Okay. Minus k.
And the M's.
Did I oops, I did fold them. Thank you. There. And then 0 minus k, and then this guy goes to 0 as well. And this is all times A, B, C, and this is away from 0. So if I multiply out that top line, what does that give me? I get 0 times A, giving me 0. I get 0. Then minus k times B, minus k times B, and then plus 0 equals 0. Okay. What does that mean? This tells me that minus kb equals 0. Therefore,
B is 0.
b must be 0. Okay, that middle guy corresponds to the big mass here. So this is the e for the eta for the big mass. The fact that this is 0 means it's going to be stationary. This means b equals 0. So this right here, this means m the big mass is stationary. Okay. What would this last line give me? Right, multiply out this last line here. 0 times A minus K times B minus 0 times C, that gives me the exact same equation. So nothing new. Now let's do this guy up here. If I do that big one there, what do I get? What do I get? So I get minus K. A. Then I get minus K big M little m plus 2K. So I'll just multiply by B, but we know what B is now. Okay, minus KC 0. And the B is equal to 0. So that goes out. This gives me minus KA equals plus AC. And this tells me that this right here. So if I write the eta for this one here, I'll write it like this. This is for omega 1. What does this equal to? This is going to be the A0 minus A. Right? Makes sense? And so that corresponds to, again, if you look at it, these two moving in like that. And this is stationary. That makes sense? Questions? Good. Hey, how do we find the next one?
Plug in the other omega squared.
Yeah, what was it again? So the omega 3 squared was what is it? K. 2. No, was the K here? Yeah, two little one big
Yes.
all over.
And
Big M little. That. Keep that into daily homework. And I think what you're gonna find from daily homework is exactly what that thing becomes. Okay. Sorry about that. Okay, so you're gonna work out this case here because I frankly I'll write it up nice and neat. It won't be due on Friday because I'll write it up nice and neat. You know, check it myself as soon as I'm happy. I mean, it's gonna work fine. But what are you gonna find with those? These are gonna go in the same direction, and this is going the opposite. Okay, that makes sense. Probably weighted by different factors. Good with that? Okay, now I want to say a little bit more about the orthogonality of these things. So for your notes to be complete. So you will work. I'll pay the 3 bar for daily homework. Okay. So I now just want to talk a little bit more general theory that I want to do the double pendulum, which is a classic case, which we have to do. Then we'll oscillator apples on Friday, and then we start doing Hamiltonians. And then after Hamiltonians, I want to put the constraints back in effectively. I can put the constraints back in, we're going to need what are called different multipliers, which are going. However, the run, you have to figure that out. I've just told everyone that. Look what I did. Look, even if they didn't want to know, I just randomly pulled people off the street and said, well, look, just it was so cool. Okay, so what are we going to do? So I'm going to talk about the orthogonality. Of the etas. Okay, so what are we going to have here? So let's assume we need a couple things here. First, we need one point. Linear algebra. Okay, if I have a whole bunch of matrices being multiplied. So I have a whole bunch of matrices being multiplied by each other, and I want to take the transpose of all of these here. So I'm going to multiply all four together and then take the transpose. Okay. What does that end up equaling from linear algebra? The transpose of all the individual matrices in reverse order. Right? There might have to be another daily homework. It's actually a non-sign summation notation. You can show that relatively fast. Okay. We're going to need that one. Also, what happens if I take the transpose of a transpose? I get the original back. Okay, so keep that in mind. So let's consider two separate normal motions. We'll say omega r and omega s. I'm using this. Let's combine J. No, I have R with this plus R and S, where omega r does not equal omega s. So they're two distinct normal mode frequencies. So what are our equations here? Our equations are this. Am I still clear? I am still clear. So I'm going to have minus omega r squared n plus v double bar, and this is going to be some eta r plus 0. Okay. So this is going to be the eta for the arc normal mode frequency. And then I'd have the corresponding thing in for s. Now, what I'm going to do is I'm going to take one of these equations. I'm going to multiply the top equation by eta s transpose. Okay. If I do that, what do I get? I get minus eta s transpose. Actually, I'll rewrite out as omega r squared eta s transpose m double bar plus eta s transpose b double bar eta r. That gives me this. It does not give it back. I've got one over here. Does that make sense? And all I did here is I pulled, since the minus omega squared bar is a constant, I just pulled this out. Okay, makes sense. Let's take the transpose of this whole thing. Take the transpose of this equation. I could this piece over here. This is a constant, I can off to the right. You tell me what the rest of this. What happens if I take the transpose of? What happens if I take the transpose of this combination? I have to take the transpose of each of these and
But in reverse.
flip them. So this one here is going to become off. Eta bar R transpose. M transpose. Now what happens if I take the transpose of this transpose?
Got the same thing.
It becomes the same thing. So this becomes eta S. Plus, now you tell me what happens to the next one. This one becomes
Eta R transpose.
eta bar R transpose, which is kind of fun to say.
B transpose.
V transpose.
Eta S bar.
Eta S bar equals 0. Okay. Now, do I know anything about the M and the V matrices?
Symmetric.
Yes. M and V are symmetric. Okay, what does it mean to be a symmetric matrix? If you take the transpose,
D equals the original.
that's just like the original. So I can rewrite that just in terms of M and V. So I can rewrite this as minus omega R squared, eta bar R transpose, M, eta S, plus eta R transpose, V, eta S equals 0. That makes sense? Now, what do I know about this fellow right here? That little bar, does this V double bar equal an S here? Does that equal anything? Yes, it does. And V double bar X and S, what does that equal? I can take this to the other side here. Right? So this substitute that V double bar theta bar S equals positive omega S squared M double bar. Right? Just by taking this to the other side. That makes sense? So this right here equals omega S squared V double bar M double bar eta S. That makes sense? Now let's put that in there. Let's see what we get. And am I still clear? The answer is yes. So this line here becomes minus omega R squared, eta bar R transpose, M, eta S bar, plus eta R bar transpose, minus omega S squared, and double bar S here. That's all it is. Hey, is there anything that's common to both of these terms?
M eta S.
More.
Omega squared.
No, the omega.
No.
Yeah, these are, this is common to both of these, right? This is common. I'm going to factor. So I can factor that out on the right. So I'll write this as omega R squared plus omega S squared, all times eta R and eta S. What do you know about this term right over here? Tell me something it doesn't equal. It doesn't equal 0. How come? Because what did we assume about omega R and omega S? They're not equal. Therefore, this term here
This should be 0.
has to be 0. Okay. So what I have here is that I have this eta R bar transpose M here. Eta S here equals 0. R is not equal to S. Okay. Now, if R equals S, this term is not 0. So what can I do? I could choose that to be 1 if I wanted to. I can just say I'm going to define that to be 1. So we can define this eta bar R transpose M eta R. And define this to be 1. You don't have to, but we could. Then is there a way of putting these two conditions together? It's 0 if R doesn't equal S. It's 1 if R equals S. That's our buddy Kronecker diagram.
How do you know it's not 0 if they are equal?
One thing that the argument here falls apart. It's if you look here that this term is on the middle. Okay. This one might be 0. But what's gonna happen is that when you basically because you have everything being positive. I mean, they're all being the same, it's kind of like having something squared. It's not gonna be 0. So this right here is a or 5 anomaly condition. For the eigenvectors. I can use that. Okay, for the normal ones. Okay. Now what happens is if this M is all the same, if it's all the same thing, you can actually show you can take this out here. So what you really have is just this eta transpose times eta S. That's just gonna be okay, that makes sense. Yep.
So in that term that
Which
doesn't
term?
the
This one?
negative omega r
Oh, here?
squared.
Yep.
Yeah. What if omega r is like negative omega s?
Okay, so this omega squared here is always going to be a positive quantity.
Oh, right.
Okay, you're never getting negative.
Oh, right. Yeah.
Okay. All makes sense. So we've just shown that the normal mode frequencies that if you look at the eta standard those orthogonally. Okay. And one more thing. The etas also form a basis. That's the idea of a basis is a really important word. What does it mean to be a basis?
You can write any vector in terms of
Any vector in terms of the linear combination of those. So what that means here is that this is any motion of the masses, not just the normal frequencies, normal mode motion. Okay, so probably I shouldn't use 80 anymore. Probably I'm using 80 is probably bad notation. Yeah, so maybe I should call something else. X. No. Q. I'll call Q. I'll keep it in. Just realize this is no longer that. This is no longer the minimum frequencies. I can write this as now some A. 1. So this is going to be basically this is going to be this eta 1 naught equal to the I omega 1 t. That's what this side is here. Then plus a B eta 2 bar with this. And this guy here is going to be the 2 bar here with this I We're gonna do T, and then like you keep on going out of all these rooms here. Okay, so what we're gonna do in the oscillating apple case, we're gonna have our apples here. So the actual, the setup we're gonna have. Is we're gonna take two strings here, we're gonna put apples here. Pretty much equal mass apples. Gonna put a rubber band here like this. Okay. And we're gonna work out this problem. We're gonna find the normal mode frequencies here. What do you think if I to say with your hands? You're gonna oscillate our apples off. We're gonna oscillate them this way. Okay. So what do you think the normal mode frequencies would be? If you were to act them out. You're gonna have this one. What else do you have? Now you have this one. Right, they're gonna be your normal frequencies. And what we're gonna say is that they're gonna form a basis. So I can write any other motion like this. So what we're gonna do is I'm gonna set up the system with these initial conditions. I'm gonna put my hand on this apple here and move this one. So I'm gonna grab hold on this apple and I'm gonna let this one swing like this. Okay. That's gonna be my initial condition. And then I'm gonna let go of this one. What we're gonna find happens is that we're gonna get this motion here. It's going to go back and forth between the two. So this one will oscillate, and that's in a little tug on this one. This will be this little oscillation. Then this one will completely oscillate. This one will be completely still. And then it's going to go back and forth. It's actually beautiful. And I told you about the physics haunted house we did at when I was at Creighton University. The guy actually had the oscillating apple set up. And he was a physics professor, but he was also an amateur magician. So there was like a magic wand there, and you're supposed to like point it and make it do this. And he'd have little kids go through there. So there was some 7-year-old or most of all going through there. Little kid had some mothers with them. Too surprisingly. And so the professor was there, his name was Tom Zeff, he passed away, but he was a fantastic guy. He went, okay, now he'd get the apples going here. Okay, now point the magic wand at this one and say stop, and this one go, and he would do that, and then the apples would do that. Well, the mother went, is he really doing that? No, it's the reasons of physics on it. And you have physics stuff. Okay, so this I'll show you how this works on. We'll set this up. We'll set up the problem. That makes sense? It's one problem. Now that said, since I don't have this set up, what we'll do is, and also when we set it up. This one here is going to be a little, I'm gonna set it up in slightly different geometry, but it's going to be the same idea, because otherwise it's a little harder to see. There's a classic problem we're going to work on, it's the double pendulum. Now I want to show you how these ideas work for the double. And it's a classic problem. Okay, so let's look at classic problem. I'm gonna have a mass here like this. This is gonna be L. This is an L. I'm here like this. This is some theta here, theta 1. And then you measure angle like this. This is the same L. This is M. And this is theta 2. Okay. So for part A, we want to find the Lagrange matrix. Find L. This is. So you tell me how to find L for that system. Again, this is one of these problems. If you don't have growing units, good luck trying to do this. If you look at a lot of books, how they set this up, I really hate how they set it up because it looks like you can only do certain types of problems and they don't show the general approach on this. So what is the general approach I always show you to do? Okay, first of all, we'll say Lagrangian always. T minus 3. Okay, I shouldn't say always, because it turns out if you do E and M, you get a different Lagrangian. It's T minus U, but U is weird. It's really this funky thing. But I addressed it. T minus 3. Now, what is kinetic energy always?
Square.
I have 1/2 M. Tell me about the V. V.
X.
How many masses do I have here? I have 2.
Two.
So you have to have a V1 square. Is I guess that might be too confusing. V1 squared plus
V2 square.
1/2 M V2 squared. You keep the same masses because they're the same mass. Okay, so we have that. So what do we know about V1? V1 is always
X dot squared.
this would be dr1 dt is like this. Okay. And so what would that be here? Then if I look at the V1 squared, this is the V1 dot. V1 dot. And what would that become? Right. This right here is really our what? It's gonna be our X dot hat of 1, Y dot 1. Right. So what does this become?
X1 dot squared.
X1 dot squared plus Y1 dot squared. Hey, what do you think V2 is going to be? Right, V2 vector. That's going to be dr2 dt. And what is this going to be? This is going to become no, I don't know. X1 that's not that at all. X2 dots X2 dot I hat plus Y2 dot J hat. Now, when you need to do this, you need an origin. So where am I taking my origin? I'm going to put it in here, but it's kind of implied. There's only 2 good spots to pick the origin. And it should be only one right now.
The wall.
We're on the wall.
Illustrated.
Yeah, this is good year. Okay, so that means that this distance right here, that is x1. This distance here, that is x2. This distance here is y1. This distance here is y2. Where'd be the other good spot that we're not going to use? Okay, it's good, but no, far lesser. Okay, yes.
Would it be at the first mass?
No, that's going to be moved. We always want our origin to be stable.
An L length down.
That would work. Okay, I'll call it like the next one down. I'd probably go to the whole length if you do the whole thing if it's just laying flat. Picking this one here. So in other words, if these were laying flat, meaning not moving, you'd have this. I'd call it if I want to, I can make that the word thing. But again, that would be this is usually the best one to do. Okay, that makes sense. Now that said, what is x1? First of all, what do you think our generalized coordinates are going to be for this problem?
Theta 1.
Theta 1, theta 2 are going to be our generalized coordinates. These are not our generalized coordinates, so we have to write these in terms of the generalized coordinates. So we're going to use theta 1 and theta 2 as the generalized coordinates. So write T in terms of them. Okay, so if we do this, what do we have? You have x1 equaling L sine theta 1. We need this distance here. This next one. And then Y one is gonna be,
Oh, cosine theta one.
and I put a minus sign in there as well. I put a minus sign in there. You're gonna be going down, so this will be this minus L cosine theta one. Hey, what is x2?
Cosine theta two.
This is x2.
L sine theta one plus L sine theta two.
Exactly. That were those all in here. It's gonna be L sine theta one. It's L sine theta two. Hey, what is y2? So now do you have what with the cosines? So the minus L cosine theta one minus L cosine theta two. Hey, what is x dot? X1 dot?
Oh, cosine theta one. Theta one and then theta one dot.
Okay, so tell me what you write. I agree that there's an L. When the time derivative of a cosine goes, of a sine goes to, it has to be the chain. So the sine goes to cosine, the cosine. Theta one. Now what do you have to do? The derivative of the interior. Time derivative of that giving
Theta one dot.
theta one dot. And what is gonna be y1 dot?
L theta one sine theta.
Yeah, this is gonna be L theta one dot 7 theta one. Hey, what is x2 dot?
L cosine theta one dot.
L theta one dot cosine theta one. Plus, same thing, but with the twos. L theta two dot cosine theta two. Then y2 dot is gonna be what? It'll be the L theta one dot sine theta one. It's L theta two dot cosine theta two. Now what do we have to do with our x dots and our y dots? We have to form these velocities squared. We're gonna have to square these guys and add them, and square these guys and add them. Hey, just see a problem with square these guys and add them? We're gonna get weird cross terms. Okay, so what's gonna happen is that these guys are gonna be squared, it's gonna be an add-on. Beautiful. When we do this, a lot of it's gonna be good. Okay, will look great, but we're also gonna get these weird cross terms. And that's gonna be run through, it's what was gonna cause a coupling between the equations. In other words, the coupling between the theta one and the two. But that we'll have to wait till Friday. Okay. Have a good day.